Hello, everyone. My name is John Zammit, and I'm from the Education and Product Support team at SNOMED International. Today, I'll be presenting the SNOMED CT and Data Analytics tutorial. And although this tutorial is about analytics, it is also about the expression constraint language, because ECL is such an important consideration when performing analytics over SNOMED CT coded health records. We'll start with a quick introduction, and then we'll explore a range of techniques that can be used to analyze data coded with SNOMED CT. After that, we'll take a closer look at how we can use the expression constraint language to create some interesting clinical queries. Next, we'll have a data analytics demonstration for you, and then we'll talk a little bit about how the expression constraint language has evolved over time. At the end of the tutorial, we'll have some time for questions and discussion. Let's begin by reviewing some of SNOMED CT's key design features, which can help to support data analytics. SNOMED CT's core features include concepts, descriptions, and relationships. SNOMED CT uses concepts to represent clinical meanings. This in turn allows us to create queries that are based on the meaning of things, as opposed to the words we use to describe them. SNOMED CT's descriptions help us to search for concepts by providing different ways of referring to each concept. This can enhance string matching in natural language processing tools and provide multilingual support for queries through translations. Lastly, SNOMED CT's relationships support queries that can use the definition of concepts, queries that require aggregation to be based on the meaning of the codes, and queries over the detailed content stored in EHRs using more abstract concepts. SNOMED CT also has a range of other features that are useful for data analytics. This includes SNOMED CT's concept model, which provides rules for defining and querying the terminology's clinical meaning, SNOMED CT languages, such as compositional grammar for creating expressions, the expression constraint language for querying SNOMED CT, and templates for defining patterns of expressions and queries. Reference sets provide a standard way of representing subsets of SNOMED CT codes, which can be used to define query criteria. They can also be used for maps and to define language preferences. And description logic provides the formal foundation for SNOMED CT. It helps to support the computational reasoning, which is an incredibly powerful design feature for data analytics. SNOMED CT's broad scope allows you to query across different disciplines, specialties, and clinical areas. It has a robust versioning mechanism to help manage queries over health records collected over a period of time. And SNOMED CT is international to support data sharing and queries over international datasets. And it also has localization mechanisms to support more locally specific queries. And now, let's explore how those design features of SNOMED CT are used for data analytics. As the focus of today's tutorial is data analytics, let's consider what we mean by data analytics in the healthcare space. Data analytics can be broadly defined as the discovery and communication of meaningful patterns in data. It's all about extracting useful information from healthcare data and applying this to describe, predict, and improve performance, whether that's clinical performance, service delivery performance, or public health management performance. And the insights gained can be used to recommend action or guide decision-making. Data analytics can be performed over health record data for an individual patient or an individual healthcare worker, patient groups or cohorts, which might be based on a combination of demographic and clinical criteria, or analytics can be performed over enterprise groups based on specific healthcare teams, wards, clinics, or institutions. And finally, over geographical groups, which might be based on a local area, a town, a region, or a particular country. The substrate is the data being analyzed, and this can range from unstructured free text, such as clinical notes or letters, to structured documents, such as a discharge summary, which might use SNOMED CT or other code systems, or to big data, which can include a combination of both structured and unstructured data. The diagram on this slide summarizes the three main purposes of analytics over patient data. First, clinical assessment and treatment, which benefits individual patients and clinicians. Then, the data that's collected for individuals, which can be grouped together for population health to benefit larger groups of people. And lastly, evidence-based clinical research, which in turn can lead to improvements in treatments for individual patients. Later in the presentation, we'll talk a bit more about these three types of data analytics. Before you can even start using SNOMED CT for data analytics, you first need to make sure that your clinical data is coded using SNOMED CT. If your EHR system records SNOMED CT natively in the records, then you can get started right away. But if your patient records use other code systems or free text, then you first need to map to or encode that data with SNOMED CT. SNOMED CT is often used as a common reference terminology to integrate and standardize data that uses different code systems to enable cross-domain queries and analysis. Once you have your clinical data coded using SNOMED CT, there are a number of different techniques you can use to perform data analytics, ranging from very simple to very advanced. For example, the simplest approach is to compare each code stored in your patient record to see if it's a member of a particular subset that you've designed specifically for your query use case. You can also use subsumption to check if a code is a subtype of another particular clinical meaning. You can use a concept's defining relationships to match against some query criteria. You can use expression constraints, and note that this is now considered the recommended technique when performing analytics over SNOMED CT coded health records. And you can use SNOMED's description logic for even more powerful reasoning. In the next few slides, I'll explain how each of these techniques work. The subsets technique is the simplest. For example, you may want to find all the patients with a tuberculosis disorder. To do this, you can create a subset of tuberculosis disorders that you want to look for in the patient records. Then you can scan through the patient records, looking at the diagnosis and checking to see if it's in the subset. In this case, tuberculosis of spinal meninges is in the subset, so this patient matches the query. The next technique is subsumption. Subsumption is when one concept is a subtype of another concept. So this approach uses SNOMED CT's hierarchy. As an example, let's consider a small population of people who each have one of these four types of disorders, coded using SNOMED CT: viral pneumonia, bacterial pneumonia, tuberculosis of respiratory system, and suppurative otitis media. These disorders are organized within SNOMED CT's polyhierarchy, which has been simplified for this example. Suppose we want to identify the people with a respiratory disease. This means that we have to identify the descendants of the concept disorder of respiratory system, and then count how many people within our population are associated with any of the descendants. And by the way, this is one of the key differences between SNOMED CT, which is a clinical terminology, and classification systems such as ICD, in which each code is only allowed to belong to a single category. So in ICD, each of these diseases is either a respiratory disease or an infectious disease, but it can't be both. So you can't look at it from two different perspectives. With SNOMED CT, if we want to identify the people with bacterial infections, we find all the descendants of the concept bacterial infectious disease, including the ones that are also a respiratory disease, and then find the people with those diseases. Or we could identify people with pneumonia. So you can see that it's easy to use the hierarchy in SNOMED CT to group together patient records at different levels of granularity and different perspectives, depending on what information you're looking for. Next, we're going to use SNOMED CT's defining relationships to create queries. This involves filtering the concept codes that we're looking for based on the value of that concept's defining relationships. So here's an example of a concept, infective pneumonia. It has 3 relationships. Infective pneumonia is a type of infection, infective pneumonia is a type of respiratory disease, and infective pneumonia has a finding site of lung structure. So we can query on any of these relationships. Infective pneumonia also has a number of subtypes, including viral pneumonia. And viral pneumonia has all the same relationships as infective pneumonia, plus the additional causative agent relationship to the virus organism. We might, for example, query our patient's health record to find all the diagnosis codes with a finding site that is a type of lung structure. And this should match on over 1,000 different codes, including infective pneumonia and viral pneumonia. Now let's look at a small example to see how this works. In this example, we want to retrieve all the disorders with a finding site of kidney. So if we run this query against this small substrate of concepts, then we can see that there are 3 concepts with a finding site of kidney: renal cyst, benign tumor of kidney, and renal abscess. And then we might want to do a second query to match on all those findings which have a benign tumor morphology. So we're looking for concepts with an associated morphology of benign neoplasm. If we run this query against our small substrate of concepts, we can see that there are 3 concepts that match this query. They are benign tumor of kidney, benign neoplasm of bladder, and benign tumor of lung. And then, if we combine these 2 queries together, we can find the concepts which have both a morphology of benign neoplasm and a finding site of kidney. We see that there is only one concept in our substrate that matches both criteria, and that is benign tumor of kidney. And we can define this query using the next technique, which is to use the expression constraint language, or ECL. ECL can be used in combination with the other techniques we mentioned, including subsets, subsumption, and defining relationships. You'll soon see why as we work through this tutorial. ECL is a formal syntax that allows us to query SNOMED CT to find a matching set of concepts or expressions. It uses a single $n sign to represent the subtypes or descendants of a concept, and a double $n sign to represent the subtypes of a concept plus the concept itself. So this expression constraint here finds all the descendants of disease with an associated morphology that is either a descendant of benign neoplasm or the concept benign neoplasm itself, and a finding site that is a descendant or self of kidney structure. If we execute this query against the July 2021 international release of SNOMED CT, we find that there are 24 concepts that match this query. And we can see a few of those concepts in the table on this slide. Now, we're going to use the ECL query we created before to analyze some patient data. We're going to look for those patients from our EHR where the diagnosis is a benign neoplasm of kidney. So here's our query expansion. We use this expansion and step through our patient records one at a time to check if their diagnosis is in the ECL expansion. And we find that patient 2, patient 6, patient 7, and patient 9 have all been diagnosed with a disease which is considered part of the ECL expansion. And so these patients match the search criteria. And the last analytics technique in our list is to use description logic. As I explained earlier, description logic provides the formal foundation of SNOMED CT. And so this description logic work is usually already done for you Because when you download a new edition of SNOMED CT, it should have already been classified with a description logic reasoner. And this classification process that gets done for you generates all the new inferences from the stated relationships that the authors created. And so you get the benefit of description logic whenever you use or query the inferred relationship in the relationship file. But there are some cases when you may want to add new content that hasn't already been classified, such as new post-coordinated expressions. And in those cases, you may need to use a DL reasoner yourself to give you the extra power that the formal logic brings. Description logic enables the validation and quality control of the terminology. It automates the reasoning and provides more powerful analytics operations, such as testing subsumption with expressions, inferring new relationships, using transitive properties, property chaining, and general concept inclusions. There are a range of DL reasoners available, including Fact++, ELK, and SnowRocket, and a number of ELK query languages, such as Sparkle and DL Query. If you'd like to learn more about SNOMED CT's use of description logic, you can refer to snomed.org/owl or snomed.org/LPS. Now, these are the three broad categories of data analytics tasks we showed you earlier. So here are just a few examples of the kind of tasks that SNOMED is used for in each of these categories. For clinical assessment and treatment, SNOMED CT is used to generate summaries of a patient's clinical history, to generate point-of-care reports for reminders, identifying care gaps, and reporting to disease registries, and for clinical decision support, to provide alerts, diagnostic support tools, or links to clinical guidelines that are relevant to a specific condition. For population health, SNOMED CT is used to perform trend analysis, which could be used to detect the incidence or prevalence of a disease or treatment, to predict demand, or to effectively allocate healthcare resources. It's used for pharmacovigilance to monitor adverse effects of medication products, and clinical audit to improve patient care by reviewing the care that's delivered against defined standards. And for clinical research, SNOMED CT is used to help identify clinical trial candidates, to predict the probability of disease, and for other research tasks, such as semantic searching over medical literature that's been tagged with SNOMED CT codes. Let's explore these tasks in a little more detail, starting with point-of-care analytics. SNOMED CT has been used for historical summaries. This is where we provide a summary of a patient's clinical history by aggregating and grouping up codes within their health record. It also allows us to aggregate patient records from various institutions, different information models, and code systems. SNOMED CT is used for point-of-care reporting, so this helps clinicians to remind them of preventative services, which patients need a reminder, or who may not have had a particular review procedure or screening procedure within a certain time. This helps to identify patients with care gaps and risk factors. And one recent example, of course, is the COVID-19 situation, where risk factors have been identified for the outcomes of COVID-19 patients, and SNOMED CT has been used in a number of research studies to help identify patients with those risk factors. SNOMED CT also helps to monitor patient compliance with prescribed treatments and to report clinical data to disease registries. SNOMED CT is also used for clinical decision support, and we won't talk too much about this now because we have a few slides later which will explain a bit about how SNOMED CT is used in clinical decision support alerts, linking to clinical guidelines, and so on. SNOMED CT is also used for a number of applications across the world for population analytics for trend analysis. This is about extracting and identifying patient patterns or trends in the data to detect changes in incidence and prevalence of disease, a treatment, a procedure, or interventions over time. It's also used for population health monitoring, monitoring prediction of demand, and effective resource allocation. As SNOMED CT has such a broad scope, it's also useful for queries that need to span over diseases, symptoms, lab results, medications, devices, procedures, allergies, and body sites. And this broad domain coverage makes it suitable for things like pharmacovigilance. Pharmacovigilance involves the collection, detection, assessment, monitoring, and prevention of adverse effects with pharmaceutical products, and it looks at the patient journey and helps to identify issues that arise within the patient journey. Lastly, clinical audit can be used to improve patient care and outcomes through systemic review of care against defined standards, and then implement change based on what was learned and discovered. For example, how many patients with ischemic heart disease are receiving the appropriate drug treatment? And lastly, clinical research is the third broad category. SNOMED CT is used for identifying clinical trial candidates. For example, candidates with a disease associated with a particular anatomical site, or patients taking medications with specific ingredients or drugs. There are a range of criteria that can be used to identify clinical trial candidates. And SNOMED CT can help when it comes to predictive medicine. This is predicting the probability of a disease and implementing measures to either prevent or significantly decrease the impact of that disease. For example, lifestyle modifications or increasing surveillance. And the third example of clinical research is when SNOMED CT is used for semantic search. Now, this is where we have large bodies of medical literature and it's tagged with SNOMED CT codes. By tagging the literature and clinical knowledge with SNOMED CT codes, this in turn allows us to utilize SNOMED CT's hierarchy and defining relationships to find medical research which relates to what we're interested in. For example, finding articles related to inflammatory bowel disease, or does the patient's medical record suggest heart rhythm disturbance? Then using the clinical literature to inform the treatment of the patient. Now, going back to clinical decision support, let's look at an example of how SNOMED CT can help to implement this service. For example, imagine we have a patient, John Smith, and he has been diagnosed with pneumonia. And a clinician is just about to prescribe a new drug to treat the patient's condition, amoxicillin 500 mg tablet. However, upon prescribing this drug, we have a clinical decision support rule which checks to see if the patient has a penicillin allergy. And in this case, John Smith does have a penicillin allergy. So then an alert is displayed to remind the clinician of the allergy, and perhaps provide a mechanism to search for safe alternatives. Let's have a look at how SNOMED CT can help to implement the clinical decision support logic you saw on the previous slide. In this case, we're leveraging SNOMED CT's defining relationships, as well as the hierarchical structure. The definition of this concept tells us that the product amoxicillin 500 mg oral tablet contains the substance amoxicillin. And if we navigate up the substance hierarchy, we find that the substance amoxicillin is a type of penicillin. Note that this is something we could determine with a simple subsumption test. Therefore, by using the defining relationships and the subtype hierarchy of SNOMED CT, we are able to identify that any drug which has a precise active ingredient of penicillin or any of its subtypes should not be prescribed to this patient. SNOMED CT concepts can be applied to clinical guidelines as semantic metadata tags to indicate that the guidelines are relevant to particular clinical situations. For example, we might apply a tag which says this guideline is relevant for diagnosis of asthma, the disease, or an asthma management regime, or an asthma control questionnaire. And we can think of the tagged clinical guideline as a document, with the guidelines themselves appearing in the body of the document, and the concept identifiers appearing in the document header as metadata. Note that in this case, we are linking from the clinical guidelines to SNOMED CT, but links can also go in the other direction, to link SNOMED CT diagnosis codes to additional information that should be collected, or to related conditions that may link to other more specific guidelines. When providers of clinical reference material tag their guidelines using SNOMED CT, This makes it easier for clinical decision support developers to locate their content and apply it in their decision support systems. Electronic health record systems, which are designed to use clinical guidelines marked up with semantic tags, can display the relevant guidelines to the user when a user selects and records an appropriate relevant concept in the health record. On this slide, we have a generic template that can be used in an EHR system to facilitate the display of an appropriate clinical guideline when a relevant diagnosis is recorded. For example, this template could be used on a clinical guideline that has the semantic tag for asthma, generating the following CDS rule. If a clinician selects a diagnosis of chronic asthma bronchitis, the asthma management guideline could be displayed on the screen because chronic asthma bronchitis is a subtype of asthma. This approach enables contextually relevant clinical knowledge to be presented to the user based on the specific codes recorded in the patient's health record. Now, let's explore the expression constraint language in more detail, as ECL is considered the recommended technique when performing analytical queries over SNOMED CT coded health records. A SNOMED CT expression is a structured combination of one or more concept identifiers used to represent a clinical meaning. For example, to represent a right hip joint, we could use the expression hip joint with a laterality equal to right. There are four main use cases for SNOMED CT expressions: representing clinical meanings in health records, exchanging clinical meanings in messages, stating the definition of a pre-coordinated concept, and mapping from clinical terms or code systems to SNOMED CT expressions. The important thing to remember here is that an expression is used to represent a single clinical meaning. SNOMED CT expression constraints, on the other hand, are computable rules that can be used to define a bounded set of clinical meanings. For example, to represent the set of lung disorders where the associated morphology is a type of edema, you can write descendant of disorder of lung with an associated morphology which is a descendant or self of edema. The single less than sign indicates that the matching concepts must be a descendant of disorder of lung, and the double less than sign indicate that the matching attribute values can either be a descendant of edema or the concept edema itself. When applying this constraint to a substrate of pre-coordinated concepts, we may find these concepts from toxic pulmonary edema to adult respiratory distress syndrome are valid with respect to this constraint. All of these concepts are descendants of disorder of lung, and they also have an associated morphology which is either edema or a descendant of edema. SNOMED CT expression constraints can also be executed against expressions. If you have an expression repository or a set of expressions, you can check each of the expressions to determine if they conform with the expression constraint. Here are three different expressions in close to user form that conform with the expression constraint. But please note that before you can execute ECL over an expression repository, you must transform your close to user form expressions into classifiable expressions and then classify them so that the ECL runs over the necessary normal form. For more information, please refer to the Introduction to Post-Coordination tutorial. Expression constraints may be used for a range of different purposes, including terminology binding. For example, if you have a data entry form and you want to restrict the values that can be entered into specific data fields to a particular hierarchy, they can be used for intentionally defining a value set. This is where the members of the set are defined by a computable rule. As we have already seen in this tutorial, they can be used to query SNOMED CT, and as a result, query health records that were coded with SNOMED CT. And lastly, expression constraints are used to help define the SNOMED CT concept model, more specifically, to define the domains and the ranges. Here's an example of another expression constraint that represents the clinical findings and members of the cardiology reference set, which have an attribute group, which is either an associated morphology of infarct or a subtype, or are associated with myocardial infarction or one of its subtypes. Let's now have a closer look at the various parts of this expression constraint so we can discuss the syntax. In this expression constraint, there are two focus concepts. The first is preceded by a constraint operator, and the second is preceded by a member of function. They are joined together with a conjunction. Everything after the colon is the refinement. And this refinement has two attributes, which are part of the same attribute group. The attributes are joined using a disjunction. Each attribute has an attribute name, which may be preceded by an attribute operator, and by an attribute value, which may be preceded by a constraint operator. To learn more, please visit snomed.org/ECL. When you're creating expression constraints, it's important to understand the SNOMED CT concept model. The concept model defines the rules for which attributes can be used and applied in the definition of a concept, and which hierarchies and which values can be used with each attribute. In order to construct an expression constraint, it's important to know those rules so that our expression constraints can work within the bounds of the rules. And one way of finding these rules is by using the machine-readable concept model. The machine-readable concept model represents the rules of the SNOMED CT concept model in a computable or machine-readable form. And this includes the domains of each attribute, the ranges or the values that can be used, how they should be grouped, and what the cardinality is in terms of how many times an attribute can be used within the definition of a concept, and how many times an attribute can be used within a single role group. The machine-readable concept model is published and versioned with each release of the SNOMED CT International Edition. And you can access the MRCM in a number of ways. First of all, you can access it through the reference sets that are included in the International Edition. And the second way to access part of the MRCM is through the editorial guide. If you browse to snomed.org/EG, you'll see in the authoring chapter of the editorial guide the specific domains that allow attributes and defining relationships. These have an attribute table summary, and in that attribute summary, it shows you what attributes can be used for that particular domain and all of the various constraints that are defined within the concept model, including the range constraints. So this can help you when you're creating expression constraints that query over a particular SNOMED CT edition. But note that the editorial guide includes these rules for pre-coordinated content. So if you're querying over pre-coordinated content, these are the rules that were used to define that content, and this can help you when you're constructing your query. If you're querying over both pre- and post-coordinated content, it's worth noting that sometimes expressions or post-coordinated expressions can have a broader set of rules. They might have a broader range for a particular attribute and allow more possible values. In that case, it's important to identify those concept model rules that apply to expressions as well. So if we are querying expressions, you can find the full machine-readable concept model through the SNOMED CT browser. So let's have a look at that full version of the MRCM. When we visit browser.ihdsdotools.org, you start off with a browser landing page, and then you'll see here that there is a button underneath the International Edition called the MRCM browser. And if we click on that button, this will take us through to the MRCM browser, which shows you the range of different domains that can have attributes applied to them. For example, If we click on clinical finding, we see here in the middle column what attributes can be used in defining concepts in this domain. So here are all the attributes used for defining clinical findings. We see associated morphology, finding site, has realization, interprets, and so on. Now, most of the rules apply to all SNOMED CT content, but there are a few rules that can apply to just pre-coordinated content or just post-coordinated content. So it's important to check your substrate, that is the SNOMED CT codes you're querying against, to see whether you're querying pre-coordinated or post-coordinated content. And so, if we click on Finding Site, all SNOMED CT content, I can see here at the top of the right column, the range of the finding site attribute is the descendants or self of anatomical or acquired body structure. Therefore, these are the values that can be applied for the finding site attribute in the clinical finding domain. So that's just a quick look at how you can use the MRCM browser to identify which attributes you can use in an expression constraint. We're going to demonstrate a process that you can use to create expression constraints that are concept model compliant. Let's say, for example, that we wanted to write an expression constraint to help us identify all the cancers that affect the gallbladder. The first thing we need to do is to determine the domain of the focus concept. Now, in this case, we're going to start by looking at the descendants or self of cancer. So step one is to determine the domain of the focus concept, which in this case is cancer. To do that, we can go to the SNOMED CT browser and we can have a look at the parents of cancer and browse up the hierarchy until we find the top level concept. And we can quickly show you how to do that. If we head over to the browser and search for cancer in the International Edition, we should find what we want. In this case, malignant neoplastic disease, the disorder. And if I click on the concept, I can see on the right side of the browser that the direct parent is neoplastic disease. But if we open up the parents and walk up the hierarchy, we can see that malignant neoplastic disease or cancer is a type of clinical finding. So that tells us the domain that we're working in. Once we know the domain, in this case, clinical finding, the next step is to determine the set of valid attributes that can be applied to that particular domain. Now for this, if we're querying pre-coordinated content, we could go to the editorial guide. But if we're querying post-coordinated content, or a mix of the two, then we should look for the rules in the MRCM browser. So let's go there. We need to select the clinical finding domain and have a look at what the valid attributes are for that domain. And we're going to choose one for this expression constraint. So we're going to choose finding site and then add that into our expression constraint, because we know that clinical findings can have a finding site. Once we've chosen our attribute, the next step is to choose a valid range. As we saw in the previous example, the MRCM indicates that finding sites can be a descendant or self of anatomical or acquired body structure. If we look at gallbladder structure in the SNOMED CT browser, we can see all the subtypes of gallbladder. And these are the body sites we are interested in. Furthermore, if we browse up this subhierarchy, we can see that gallbladder structure is an anatomical or acquired body structure. So we're going to choose descendants or self of gallbladder structure as the value of our attribute, because we know that this is concept model valid. And now we know that our expression constraint is compliant with the concept model, and it will help us to find the concepts that have been defined using these same rules in SNOMED CT. Once again, please remember this important hint when using the concept model rules. Make sure you select the content type based on the substrate being queried, which, as I mentioned earlier, is whether or not you're querying pre or post coordinated content. Now, most of the rules apply to all SNOMED CT content, but there are just a few that apply specifically to pre or post coordinated content. The expression constraint language has many other features that you can use to focus on specific content in SNOMED CT. For example, you can find the direct children of a concept using the less than sign with an exclamation mark. You can find the ancestors of a concept using the greater than sign, the members of a reference set using the hat symbol. An asterisk or star can be used to represent any concept in a SNOMED CT edition, and you can use this anywhere in your query that a concept is used. There is conjunction, disjunction, and exclusion using and, or, and minus. Cardinality restricts the number of times a matching relationship can appear. And there are other features, such as the reverse flag and dot notation, which allow you to reverse the direction of the relationship to select attribute values rather than the source concept. In a moment, we're going to show you some examples, but you can always access the full specification at snomed.org/ECL. Let's now have a look at some example ECL queries. And for this, we're going to use the ECL Queries tab in the SNOMED CT browser. If you'd like to try these examples yourself, you can visit browser.ihdsdotools.org and use the Expression Constraint Queries tab, where you can build and execute expression constraints. The expression constraint we're going to start with is one we showed you earlier in the tutorial. If you recall, we looked for lung disorders with a morphology of any type of edema. So we had the descendants of disorder of lung with an associated morphology that's equal to the descendants or self of edema. So now we'll go over to the SNOMED CT browser and demonstrate how we can build and execute this expression constraint. Now here we are on the Expression Constraint Queries tab of the SNOMED CT browser. Now if you've already constructed your ECL query, you can simply copy and paste it into the field labeled Enter an Expression, and then click on Execute. And as we can see here, there are 30 concepts in the expansion of this query against the July 31st, 2021 International Edition. And if we click on one of the members of the expansion, we can see that the definition of the concept satisfies the constraints we included in our ECL query. So for example, with acute pulmonary edema, we can see that it's a subtype of lung disorder and it has an associated morphology that is a descendant or self of edema. So that is why this concept is in the result set. For those who are new to ECL, another useful feature that the browser provides is the ECL Builder. I will now clear my previous query and click on the blue button to show you how that works. So we're looking for lung disorders with a morphology of any type of edema. In this case, lung disorder is going to be the focus concept. So I'll search for lung disorders by entering some partial terms and select disorder of lung. And you can already see at the bottom what the corresponding ECL syntax looks like. In this case, I might change the default of descendant or self to descendant of. But we know that in this case, I'm not just looking for lung disorders, but a specific type of lung disorder. Ones where the associated morphology is any type of edema, which is a refinement. So now I'm going to click on Add Refinement. First, I will search for the attribute, associated morphology, and then I will select that. And then I will search for the attribute value of edema and select that concept. One nice thing about the ECL Builder is that it uses the machine readable concept model to help us build expression constraints that are concept model compliant. So for example, because we chose a disorder as our focus concept, we are restricted to attributes which are valid for clinical findings. And when we chose the attribute associated morphology, we are then limited to concepts from the morphologically abnormal structure subhierarchy to choose as the attribute value. This can be extremely useful, especially when we have cases where we have non-unique descriptions which may be part of a subhierarchy which is not relevant to the concept model. For example, this would help to ensure that I choose laceration, the morphologic abnormality, as opposed to laceration, the disorder. Once we are satisfied with the output of our ECL query, we can click on OK and then execute the query in the same way as we did before. And you can see here that we have the same expansion with 30 concepts. We're now going to look at descendants and ancestors functions using the concept fracture of femur as our focus concept. And I'll just copy the first example here to my clipboard so I can show you how these work in the browser. First of all, descendants of fracture of femur uses a single less than sign. And as you can see, we have 136 concepts in the expansion. And if I add one more less than sign, we get the descendants or self of fracture of femur. Naturally, when we expand this one, we get one more concept in the expansion, because this now includes the concept fracture of femur itself. If we want the direct children of fracture of femur, we can use the exclamation mark after the single less than sign. Here we have only 12 concepts in the expansion, because these are the immediate subtypes. Now if we want the ancestors of fracture of femur, we can use the single greater than sign. And there are 25 concepts in the expansion here. One more greater than sign to get to the ancestors or self of fracture of femur, which yields 26 concepts in the expansion. And finally, for the direct parents of fracture of femur, I will use the greater than sign followed by an exclamation mark. And this gives us just two concepts in the expansion. So that's how descendants and ancestors work. And note that newer implementations of ECL may also support direct children or self of and direct parents or self of, using double less than sign and an exclamation mark, and double greater than sign and an exclamation mark. We'll now explore how conjunction, disjunction, and exclusion work. We'll go through some of these expression constraints, but note that the tutorial slides will be made available later so you can execute these queries on your own against the International Edition or one of the national editions. There are some concepts in SNOMED CT that are both a device and a pharmaceutical biologic product. These are the drug-eluting stents, which are devices that also have a drug component to them. So this query will help us identify anything that is both a product and a device. Note that by using AND, we need to satisfy both of these conditions. And once we execute this query, we see that there are 15 concepts that are both a device and a medication. Now, if I change the AND to an OR, we get anything that is either a product or a device. And when we execute this query, we see that we have a lot more concepts in the expansion, because now we have all the concepts that are subtypes of pharmaceutical biologic product, and we have all the devices. So by using OR, we only have to satisfy one of the conditions, hence the larger set. We can use minus in the following query to determine the products that are not devices. And this expansion is 15 less than the expansion of just the drugs, because we are subtracting those 15 combination concepts. In this example, we're going to use OR as part of the refinement to identify procedures that have either a direct site or a direct device. And note that we're using wildcards here. And here we use minus in the refinement to find clinical findings with an associated morphology of hemorrhage without hematoma. Note the use of brackets around the attribute values to indicate nesting. On this slide, we have some examples of role grouping. You can use role grouping within an expression constraint to define whether the criteria you're checking appears in the same relationship group or whether it appears anywhere in the definition of a concept. Note that relationship groups are often referred to as role groups. To illustrate how role groups work, I'd like to start by showing you how we can identify procedures that have both a direct site and a direct device. We can do this two ways, with an AND or with a comma. Again, note that the star or asterisk symbol is a wildcard. So in this case, we can have any procedure site direct or any direct device. And once I execute the query, we see that we have 941 concepts in the expansion. And if we look at the definition of one of those concepts, we can see that this concept uses a procedure site direct attribute in one role group and a direct device attribute in another role group. But if I wanted to identify procedures that have a direct site and direct device in the same role group, I have to use the curly braces to indicate grouping, and I would place them around the attributes. Now, when we expand this query, we can see that we only have 123 concepts in the expansion. And if we click on one, we can see that the attribute relationships we are interested in are part of the same role group. Next, we'll have a look at cardinality. We can use cardinality to check how many times a refinement appears in the definition of a concept. And depending on where we use the curly braces, we can check within a single role group or anywhere in the definition. This ECL query will help to find diseases with more than one finding site relationship, anywhere in the definition. This one takes a little more time to execute, given the nature of the query and the size of the subhierarchy. But eventually we can see that we have over 11,500 concepts in the expansion. Now, if we wanted to find diseases with more than one finding site in the same role group, we could use this query with the curly braces placed around the refinement. And we can see that there are no concepts in the expansion, which is expected because we shouldn't have two finding sites in the same role group. So this is really an example of how you can use ECL to QA the content in an addition. Now, if I move the curly braces so that they are nested around the finding site relationship, we can find the diseases with more than one role group which contains a finding site. And now we can see over 11,500 concepts in the expansion, which is very similar to the results of the first query. Note that cardinality is often used with medications, where we need to identify drugs that have a specific number of precise ingredients. So for example, we can use this query to identify products with exactly 3 precise active ingredients. And if I execute the query, we can see that we have over 120 concepts in the expansion. And just by looking at the description of this concept, we can see that it appears to have anhydrous glucose, potassium chloride, and sodium chloride as precise active ingredients. And another set of examples here. This time we have the reverse flag and dot notation. In the previous query, the expansion generated a list of medications. But what if we were interested in the ingredients of those medications? This is where the reverse flag or dot notation can be useful. First, the reverse flag. The precise active ingredients in any calcium-containing product can be found using this query. The reverse flag looks for the destination concept instead of the source concept. So here we are selecting the values of the has precise active ingredient relationship. And now for dot notation. Here we are looking for all the subtypes of calcium-containing product. And then once we have found those products, we then find the precise active ingredient. So in summary, dot precise active ingredient finds the destination concepts of this particular attribute. And here's another example query we can use to find the finding sites of any edema. So that's the reverse flag and dot notation, which are very similar. And you can use either one. However, note that the dot notation tends to be briefer in terms of the syntax. With the July 2021 release, SNOMED International has enhanced SNOMED CT by adding the capability to express concrete domain values. This enhancement will initially target improvements to the pharmaceutical biologic product hierarchy. Now, prior to July 21, numerical values in SNOMED CT were represented as concepts to allow the drug model implementation. A concept was created to represent every number needed in the international drug model. Moving forward, clinical drug strengths will be represented as true numbers. as opposed to using the existing workaround of concepts, which represent those numbers. And this creates some interesting opportunities for ECL queries which use mathematical operators. For example, we can use this query to find all the medicinal products which contain no less than 50 milligrams and no more than 200 milligrams of acetaminophen. And note that we have specified the units as part of the ECL query. And when we expand this ECL query in the browser, we can see that we have 10 medicinal products in the July 31st International Edition, which contain between 50 and 200 milligrams of acetaminophen. And the numbers which appear as part of the preferred terms confirm that 80 milligrams, 120 milligrams, 160 milligrams, and so on. So that concludes our overview of the main features of the expression constraint language. Okay, in this next part of the tutorial, we have the analytics demonstration. And the purpose of this demo is to show you how we can use SNOMED CT's underlying logic and the expression constraint language to help support the clinical decision-making process. We're going to be running some analytical queries over sets of synthesized SNOMED CT coded health records. In other words, the patient data has been manipulated to present these scenarios. Therefore, these clinical scenarios are for demonstration purposes only, mainly to show you the value of SNOMED CT and the expression constraint language when performing analytics over coded health records. In this first example, we're going to consider a cohort of patients with the BRCA1 gene mutation. The BRCA1 gene provides instructions for making a protein that acts as a tumor suppressor. Inherited mutations in the BRCA1 gene have been linked with a higher risk of hereditary breast cancer. Now suppose we have a patient who has been identified as having a BRCA1 gene mutation, and she is contemplating whether or not to take tamoxifen to reduce the risk of breast cancer. Tamoxifen is a medication that's used to prevent and treat breast cancer, but it comes with some side effects: bone pain, hot flashes, nausea, fatigue, and others. And many patients may decide not to take this drug. But our patient would like as much information as possible to help her make the right decision. So we're going to use SNOMED CT to help understand the outcomes of other patients in a similar situation. Ultimately, we're going to define two patient cohorts. First, the patients which have the BRCA1 gene mutation and are taking tamoxifen. And second, the patients which have the BRCA1 gene mutation who are not taking tamoxifen. And then we'll compare the incidence of breast cancer between the two cohorts. And to do this, we're going to use the expression constraint language to construct the relevant subsets. We can find all BRCA1 gene mutations using the expression descendants or self of BRCA1 gene mutation positive. Note that this is a query which uses SNOMED CT's hierarchical structure. Next, we can find all the tamoxifen products using descendants or self of product containing tamoxifen, which is another hierarchical query. And lastly, we can identify breast cancers with a query which identifies specific types of diseases. Descendants or self of disease with a finding site, which is a descendant or self of breast structure, and an associated morphology, which is a descendant or self of malignant neoplasm. And note that this is an example of a query which not only leverages SNOMED CT's hierarchical structure, but also its defining relationships, specifically the finding site and associated morphology relationships. Once again, this is one of the unique advantages of using SNOMED CT for analytics. And now we'll use a tool called the Health Data Analytics Demonstrator, where we can analyze this clinical scenario. You'll notice at the top that we have two tabs. The Subsets tab is where we build our ECL queries, and the Cohorts tab is where we use the queries we've built against the simulated medical records. If we look at the Subsets tab, we can see that I've already created and saved the relevant ECL queries that we're going to need here, just to save us some time. We have the query to capture any BRCA1 gene mutation positive finding. We have the query to find tamoxifen or any of its subtypes. And lastly, the query to help us discover all the breast cancers in SNOMED CT. Now let's go over to the Cohorts tab. Before we try to answer a clinical question, let's have a quick look at the simulated patient data and talk about the relevant cohorts. We can use the ECL queries we previously created to identify the cohorts. For example, by establishing a primary exposure using the BRCA1 subset, we can determine that 1,092 patients in this dataset have the BRCA1 gene mutation. And by adding a refinement and using the tamoxifen subset, we can see that 680 of those patients were treated with tamoxifen. If I scroll down the list of patients, I can see all the different tamoxifen products that these patients were prescribed. I can also determine that 412 patients did not take tamoxifen. But what we really want to know here is how many of the patients in each cohort develop breast cancer. And for that, we need to remove the refinement and instead perform a test. First of all, we want to compare the patients who have and have not taken a product containing tamoxifen. And once again, for that, I will use the tamoxifen subset I previously saved. And then I need to determine how many of these patients develop breast cancer. Once again, I'll use the relevant subset I previously saved. And now that I am ready to perform the analysis, I will click on Run Test and wait for the query to execute before we interpret the results. Once again, we can see up here that we have 1,092 patients with the BRCA1 gene mutation. Of the 680 that took tamoxifen, 29% of those were later diagnosed with a breast cancer. But of the 412 patients who did not take tamoxifen, almost 70% were diagnosed with a breast cancer. So in summary, this simulated dataset suggests that BRCA1 patients who are treated with tamoxifen have a reduced risk of developing breast cancer at a later point in their lives. In this second example, we're going to compare cohorts of patients who have been diagnosed with COVID-19 infectious diseases and examine the rates of incidence for further complications or outcomes. The cohorts we'll be using in this analysis include patients with obesity, and note that obesity in SNOMED CT has several subtypes, and patients with two pre-existing conditions, a type of diabetes mellitus and a hypertensive disorder. In terms of the subsets that we'll need to define these cohorts and run the analysis, we have a range of hierarchical queries we'll need to use here. And here are the corresponding ECL queries. First of all the COVID-19 infectious diseases, then any type of obesity, and for the cohort with comorbidities, we need to use two ECL queries to identify patients with both conditions: descendants or self of diabetes mellitus and descendants or self of hypertensive disorder. And then we have the outcomes we want to compare. We want to determine what percentage of our patients initially diagnosed with COVID-19 later contract pneumonia and what the mortality rates are. And so for this, we'll need two more subsets: pneumonia caused by COVID-19 or any of its subtypes, and then the finding corresponding with death or any of its subtypes. And for this part of the demonstration, we have another tool we have developed at SNOMED International called Outcome Comparison, COVID-19. And you can see on the left side here, we have three sections: patient criteria, outcomes, and groups. Under patient criteria, we will indicate the base condition, which in this case is defined by the COVID-19 infectious diseases subset. So I will key in COVID-19 and choose the first concept in the search results, because this is the sub-hierarchy which contains all the COVID-19 infectious diseases. Once I make my selection, you can see the corresponding ECL query. And now we can see that in our simulated dataset of almost 1.5 million patients, we have over 215,000 who have been diagnosed with a COVID-19 infectious disease. The outcomes section is where we specify the outcomes we want to compare. So in this case, The outcomes are going to be pneumonia caused by COVID-19 and death. First, I'll key in some partial terms and then choose the first concept in the search results. And you can see the corresponding ECL query. And the next outcome is death. So again, I'll key in some partial terms and make the appropriate selection from the search results. Under the group section down here is where we establish our additional cohorts. The control group represents the cohort we have established thus far. Patients with a COVID-19 infectious disease and no additional criteria. So I'll add another cohort by clicking on Add Refinement and then choosing Finding and searching for obesity. I'll choose the first concept from the search results, and then we can see the corresponding ECL query, descendant or self of obesity. And now we can see that we have over 96,000 patients in this cohort with obesity. And note that the control group has dropped from 216,000 patients to just over 120,000 patients, indicating that the patients with an obesity have been removed from the group. This is because the control group is made up of patients who are not in any other group. And now I'll click on Show Insight, which generates these bar graphs on the right side of the screen. The blue bar indicates the percentage of COVID-19 patients who later contracted pneumonia, while the beige bar represents the mortality rates. And you can see here the data suggests that patients with the existing precondition of obesity are at an increased risk of developing pneumonia, and furthermore, their mortality rates have almost doubled. Now let's examine what happens when patients have two existing preconditions. First, I'll remove the existing cohort, and then we'll start the process of building a new cohort by clicking on Add Refinement. Once again, the cohort type is Finding, and then I'll add diabetes mellitus to the list. Before we add the second condition, let's pause for a moment and click on Show Insight. And in looking at the two sets of bar graphs, we can see that the results are similar to the obesity cohort. An increased risk of developing pneumonia and an increased mortality rate. I'll go back over to my new cohort and then click on Add to also indicate that this cohort includes patients with a hypertensive disorder. Note that this cohort indicates almost 46,000 patients. And again, the numbers in the control group have been adjusted to reflect the fact that this group no longer contains patients with the two preconditions. Once again, I'll click on Show Insight to perform the analysis and present the updated results. And now we can see an even greater difference between the bar graphs in the control group and the bar graphs associated with these patients who have diabetes and hypertension. Overall, these results indicate what one might expect. Obese patients who contract COVID-19 are at an elevated risk of developing pneumonia and have a higher mortality rate than non-obese patients. And patients with diabetes and hypertension have an even higher risk of developing pneumonia and a higher mortality rate when compared to patients without these two preconditions. So that concludes the analytics demonstrations. In terms of the important takeaways from this demo, first of all, we can use SNOMED CT and its features to perform advanced analytical queries and answer some interesting clinical questions. But this requires an understanding of how the terminology is intended to be used in an EHR and some familiarity with the ECL syntax so one can identify the appropriate subsets and cohorts. Before we conclude the tutorial, I'd like to spend a few moments talking about how the expression constraint language evolves over time. For those planning to use SNOMED CT for data analytics, it's important to know that the expression constraint language specification and guide has undergone several revisions since its inception in 2014. The table on the right of this slide highlights some of the features added to subsequent versions of the expression constraint language. For example, the ability to identify child or self of and parent or self of was added in version 1.4. By adding new features to the expression constraint language, we are able to support additional use cases which arise when new requirements for querying specific parts of SNOMED CT are identified. It is reasonable to expect additional changes going forward, but in general, changes are made in a manner which ensures backwards compatibility. It's also important to know that changes to the language and changes to the tooling are two separate efforts. In other words, when an update is made to the ECL specification, tooling must also be updated to support the new features. It's reasonable to expect that ECL tooling will not always align with the most recent version of the expression constraint language. For instance, the SNOMED International Browser ECL Queries tool implements the full set of ECL version 1.3 functions, but enhancements have been made to support filtering by term and module, and there are plans in the works to update the ECL functionality of the SNOMED International Browser to support features added in subsequent versions of the language. Let's spend a moment discussing some of the features that have been added in recent versions of the expression constraint language and what you can expect going forward. In versions 1.5 and 1.6, we introduced filter constraints, which allow us to filter the expansion based on details associated with descriptions and concepts. For example, we can identify all diseases which include the word cardio as a term prefix, and we can apply additional constraints which leverage related attributes, including language, type, dialect, and acceptability. We can also identify all the subtypes of heart disease which have a definition status of primitive. These sorts of ECL queries are often of interest to content authors. Version 1.7 of the expression constraint language, which has not yet been released, will introduce new features which allow us to retrieve more granular information that is included in a reference set. The requirements for this functionality come from mapping and historical association or concept versioning use cases. And that brings us to the end of the tutorial. If you are interested in learning more about data analytics and SNOMED CT, please refer to the links provided on this slide. We have the Data Analytics with SNOMED CT guide and the Expression Constraint Language specification and guide. And for those of you who are interested in exploring SNOMED International's educational offerings, please visit snomed.org/courses. On behalf of SNOMED International, we would like to thank you for watching this tutorial. We will now welcome any questions or comments you may have.
Hello, everyone.
Hello, everyone. Anne, are you there? It's quiet here.
I am here. Can you hear me? Can't you hear me?
I'm not able to hear you, Anne, and I'm not sure if everyone can hear me. Is your microphone muted?
We hear you.
Okay. So, hi, everyone. Thank you for joining us today on the question and answer and discussion portion of the webinar. I hope you enjoyed the tutorial and the demos that we included in the tutorial. I thought we would talk a little bit more about some of the questions that were posed during the tutorial. There's maybe a bit more that we can discuss there. So just going back to that, and unfortunately I can't hear you. I can see you, but I can't hear you. So it might make the interaction here a little bit different. But just going back to that question that Michael asked about using ECL queries with a FHIR API, that is something you can do. There is an operation in FHIR where you can expand a value set, and you can include an ECL query in that, an expression constraint language query within your expansion, so that you're actually defining the value set you want to expand on the fly. And that's something we go into quite a lot of detail about in our terminology services course where we teach people how to use a snowstorm terminology server. And the snowstorm terminology server supports, it has its own proprietary interface, which allows you to use ECL. And it also has uh, APIs for HL7 Fire. And you can use ECL in that on that interface with the expansion. Okay, just scrolling up here, looking at some of the other questions. Yeah, there was something maybe I wanted to show everyone, which kind of relates to the question Marie Alexandra posed about versioning. So I'm going to try and share my screen here. Hopefully, okay, hang on a second. I've just been asked to check the
And while
presenter
John
chat.
is
Okay.
trying to get the
Can
audio
you
to
hear me
work.
now?
Yeah, we hear you, John. Can you hear me?
Yeah. Okay.
Good. Great.
It's much better. Thanks, Anna. So can you see the screen I'm sharing now?
Yeah, we see it, John.
Okay. So Marie Alexandra was asking about which version of the expression constraint language is supported in the browser. And I mentioned 1.3, just so everyone knows, when you're using the browser and you go to the expression constraint queries tab, there's this little help button here. So this is something that you can use to determine which version of ECL the browser currently supports. As I said in the video, officially it's 1.3, but then we also have some filters you can apply to ECL queries, which behave similar to features that have been added in subsequent versions of ECL. Now, are there any other questions, Anna, that...
Yeah, just a brief run from Pim about how they can access this presentation here. And then a lot of very positive comments, so thank you all. That the presentation here will be available on the platform for the next 3 months. And people can sign up for the Expo after Expo has finalized so that they can go and see it. And you can also see the handouts. And after that, I believe we will make the presentations or the videos from the Expo available to on YouTube. So you will be able to see it afterwards.
Okay.
I'm just looking here
So I
if
see
there are
we
more
have another
questions.
question here about role groups, which are also sometimes known as relationship groups. I have an example concept here that I often use to discuss this point, which is cholecystectomy and exploration of bile duct. And if we look at the definition of this concept in diagrammatic form, we can see that it has two relationship groups or two role groups. And the reason why we use role groups in short is to organize the definition in a way that makes sense. So, for example, with this particular concept, the exploration applies to the bile duct structure, while the excision applies to the gallbladder structure. So that in a nutshell is why we use relationship groups in SNOMED CT definitions. It's really to organize the content within the definition. Did you have anything you wanted to add to that, Anna?
It's simply to ensure correct interpretation of the meaning of a concept, so that you know what attributes fit together or go together and should be understood together. If there are attributes, many of the same attributes, just as John was saying. So it's simply to help computers understand what attributes go together. And Prabhat, You have a question here. Any example of building ECL with Python or JavaScript? John, are you aware
I
of implementations
not being a
using
developer
Python?
myself, I don't really have anything to add to that question, but Prabhat, that's something that we could take that discussion offline and reach out to our technical services team,
Yeah.
maybe find out if there's some information we can share with you there. Um, I would just add that in general, ECL is supposed to be something that can be implemented in a way that's independent of the technology
Mm.
that you're using in your development platform. Um,
One thing we were sitting in the background discussing, John and I, was the importance of knowing SNOMED CT and understanding exactly what are the concepts that you use in your expression constraint in order to generate the value set. So although user interfaces are developed to help users construct these expression constraints, it's still important to have some a feel for where in the hierarchy and how deep are we when specifying constraints. So I hope that you also got that point in the last part of the tutorial, that it requires some understanding of both the content and also the concept model to construct an appropriate expression constraint to use as a value set.
right. And on a related note, that just reminded me of a presentation I watched yesterday, which was about data analytics with historical SNOMED CT data sets. So that was the presentation that Matt Cordell did, and it was really interesting because he talked about really getting to the need to explore your ECL queries in more detail and understanding exactly what content your queries are revealing, so to speak. And he got into some considerations around um, how SNOMED can evolve over time and how that can impact the results of your ECL queries. And so sometimes you have to consider things like content that's been inactivated, or we might have a sub hierarchy or content in SNOMED CT that's been moved. And so how that can impact ECL queries going forward. Um, and we talked about a bit about that in the tutorial today when we discussed how important it is to consider the substrate. So yeah.
So we have a question from Robert Wynn about any ECL to DL query examples now that SNOMED CT can be converted to OWL. So thank you for bringing in that point, because that's true. We now have all the stated relationships represented as OWL axioms in our distribution files. But to my knowledge, I'm not aware of any examples showing how the ECL would be converted to DL query, or to query over DL, I'm afraid. John, are you aware of such?
No, unfortunately, I don't have anything to add to that discussion.
No. So, but Robert, there may be, but not to our knowledge yet. So, a point for a new demonstration.
Yeah. Um,
Then,
moving on to the question by Chunyun Lee about data analytics outside of achieved by outside of querying the EHR. The only thing I can think of there is if you're using some type of data warehouse solution where
yeah.
you're extracting your EHR data
Mhm.
to another infrastructure that is more geared towards intensive queries and things
Yeah.
like that. Queries that could potentially affect performance of a system that needs to be used day to day for clinical purposes.
if you have multiple EHR systems recording data with various code systems, and you apply maps to to um, to have them all the data SNOMED CT enabled, and then transferred to an SNOMED CT enabled, I don't know, research repository. You can imagine that you would then have anonymized data and that you can run ECL over, so separate from your EHR data store.
There's a question from Abdul here, which kind of
Mhm.
it's around the area of SNOMED CT content, and
Yeah.
he's asking about a blood glucose level and why it's a procedure and not an observable. So
So
there might actually be an
if you,
observable, and
we can
I
still
think
see the browser. So if you do a search for blood glucose level, we could see the
yeah,
results.
and I can do that. But even without doing that, just to give some insight to the question, really, um, SNOMED has a broad scope. So you might have a use case where you need to record the fact that you've performed the blood glucose tests, and it would be appropriate to, in that case, use the procedure to record that. You might have another use case where you want to use an observable entity to record the result of a blood glucose level. So it looks like if we search for blood glucose in the browser and filter on observables, we have some observables to support that use case. Oh, is that sort of what you were thinking of demonstrating with that one, Anna?
Yeah,
Yeah.
just when you do a search for blood glucose level, and then you can see over in the filter by semantic tags that there
Yeah.
are many matches.
Yeah.
So there are concepts from different hierarchies that have that description. Um, so you
Yeah.
need to, when you pick your and that relates to what I said before, you need to know what concepts you're looking for. So if you want to find a procedure using the expression constraint language, the point of departure for using the descendants or self of would be that you also find the appropriate procedure concept to use in the expression constraint. Otherwise, you could end up getting a range of descendants of a clinical finding blood glucose level. So a blood glucose level finding, and that is not in what you want if you are seeking the procedures.
And that just relates to the point we were making earlier about, when you're using ECL for analytics
Mm.
against health records that have been coded with SNOMED CT, you really do have to understand how SNOMED is intended to be used and how it's been implemented in your health records so that you can identify the records of interest.
So I can see
Um,
Maria Alexandra asked about GCIs, and I thought we could actually see them. So I'm just trying to see if I
yeah,
can
I mean, not all concepts are going to use
have
GCIs. I thought I had an example of something
yeah,
that,
I'm just checking here.
yeah, you might have to point me there. There's some. I
Mm,
believe if you look at a concept which uses GCIs, you can see an indication of that. Even on the summary tab, there's some
yeah, yeah, there
indication of the
should be.
axiom. I don't,
So
unfortunately, I don't have an example concept handy here.
I'm sure if we just, I know we have some from the content team in the audience. So if you are aware of an example that we could look at, then you might write
Yeah.
it.
Ian
And while
Spires
we wait,
has a good example. I can touch base with Ian and then link up with you, Maria Alexandra, to share that.
uh,
We had a question from Jim about the
yeah,
assimilated data in the COVID-19 data set. Yeah, you might have noticed that the URL in that demo was blocked out, and that is because that is a tool that is not publicly accessible at this point, at least from a management perspective. And that I believe that's because it doesn't support simultaneous use. So only one person can use it at a time, Jim. Um, but I'm sure if you were interested, we could arrange something to give you where we would give you a private tour or let you access it for a determined amount of time. So reach out to us if that's something you're interested in exploring. We don't have much time left, so I think we're
So
going to have to end it. Ian provided his example.
yeah, if you look up the concept traumatic or non-traumatic injury in the browser.
That's it. That sounds right.
Yeah.
We're going to run out of time here, so I'm just trying to make the most of this. I've got to take my filters off. Yeah, and I think non-traumatic injury, no. No, I'm not seeing the axioms here. I was expecting something to appear over here, so maybe
Okay.
that's not a good example.
So Maria Alexandra, if you send us an email at elearning@snomed.org, we will send you back a bunch of examples to show you.
Okay, we've now gone over the allotted time. So thank you everyone for joining us. Any queries to the education team can be sent to elearning@snomed.org, and we would encourage you to watch the other tutorials and all the presentations and e-posters that were included in this expo. So thank you very much for your time and have a great day.
Bye all.
Bye now.